Principles of Bioproduct Separation, Module 12, Crystallization, Segment 2, Crystal Size Distribution. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. We have previously discussed about basic concept of crystallization. In this segment, we will discuss about crystal size distributions. Crystal size distribution in a crystallizer can be described by mass and energy balances because crystallization produces not only a single homogeneous lump of solid, but a slurry of discrete particles of various sizes. Population density. A typical crystal size distribution is described by a population density as shown in the figure. The abscissa in the plot is the characteristic size L, and the ordinate N is the number of crystals per volume between size 0 and L. The slope of this plot, which has dimensions of number per length, is called the population density and as described by equation 11. At small times, N is significantly non-zero, only near a small size, possibly as the result of shading. At larger times, N slowly gets smaller. Population density can be used to calculate fractional moments of distribution as shown in equation 12. If J equals to 0, the moment corresponds to the fraction of the total number of crystals between size 0 and size L as shown in equation 13. If J equals to 3, the moment corresponds to the fraction of the total mass of the particles between size 0 and L as shown in equation 14. The use of the population density is best approached by analyzing the operation of a continuous crystallizer as shown in the figure. Such a unit operates at steady state. The crystallizer is fed continuously with solution which is at constant concentration but contains no crystals. The product stream is removed continuously at the same rate as the feed. The crystal size distribution within the vessel is identical to that in the product slurry or magma because the unit is well mixed. It is assumed that no alteration of the crystals occurs. We can now make a balance on the number of crystals within a given size delta L as shown in equation 15. Because the crystallizer is operating in steady state, the accumulation is 0 as shown in equation 16. As delta L approaches 0, equation 16 becomes equation 17. If we assume that the growth rate G is not a function of the size L, equation 17 becomes equation 18. When L is small, the population density will be dominated by the nucleation of new crystals as shown in equation 19 and equation 20. The mass for a given size range is described by equation 21, whereas total mass of crystals can be calculated using equation 22. Change in the fraction of crystal mass can be calculated using equation 23. If the derivative of equation 23 with respect to L is set equal to 0 and solve for L, the maximum or dominant size can be calculated using equation 24. This characteristic size is often used as the basis for the crystallizer design. In the next segment, we will discuss about batch crystallization. Until then, I am Yusuf from Institut Teknologi Bandung.